Hello class, today we'll be looking at the general term of a sequence for the second time. We're going to cover something a little bit different. We're going to do a calculation of the formula for the general term of a geometric sequence. For those who remember, a geometric sequence is a sequence where each successive term increases by a factor of a certain amount. In other words, it's multiplied instead of added. And we're going to look at recognizing number patterns for diagrams. Something we've already done, but we're going to look at in a little more detail. Okay, let's go through an example first to find out how we can get the general formula for a geometric sequence. So if we look here, we find that we have a geometric sequence. Now, the reason why we know that is because for each figure number, n, when we have t1, our value is 3. For t2, our value is 15, which we can also write as 3 times 5. Okay. It's been multiplied by 5. Okay. Now, when we go from 15 to 75, when we go to our third term, we also know that it's multiplied by 5 because 15 times 5 is 75. So we can write this as 3 times 5 times 5. Okay. Lastly, we're going from 75 to 375. Same thing, we're multiplying by 5. Okay. And T4 is just 3 times 5 times 5 times 5. So we can rewrite the formula as Tn equals 3 times 5 n minus 1. Now, notice that we have the n minus 1 again, just like with the arithmetic sequence. Now, the reason for that is, on our first term, when we have t1, our value is simply 3. Okay? That means if we plug in the 1 here, we have 3 times 5 to the power of n minus 1, 1 minus 1, okay? And that will equal, t1 is 3 times 5 to the power of 1 minus 1. In other words, that's 3 times 5 to the power of 0. And if you remember what we've learned in previous lessons, way back at the beginning of the course, we know that any number to the power of 0 is 1. So t1 would be 3 times 1, which is 3. Okay. It always helps to verify your answers. Okay. So we can try the formula for other values of n. Let's say t2. t2 would be 3 times 5 to the power of 2 minus 1. And that would simply be 3 times 2 minus 1 is 1, so we just have 3 times 5, which is 15. Okay. We can also look at t4. We have t4 equals 3 times 5 to the power of 4 minus 1. Okay. We know that 5 to the power of 4 minus 1 would be 5 to the power of 3. 5 to the power of 3 is, of course, 125. And 3 times 125 would be 375. Okay. So you can verify right here by referring back to the sequence. We know that the fourth term of our sequence is 375. The second one is 15, and the first one is 3. Okay? So it always helps to verify your answer. Now let's take a look at our second example. Now here we have a diagram with dots. Okay? First we can count here 2 dots. Okay. If we count over here, we have 8 dots. Here we have 3, 4, 5, 6, 1, 2, 3. 3 times 6 would be 18 dots. Okay, and here we have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 4 times 8, 32 dots. Okay. Now, how can we find a pattern from this? Okay. When we have shapes, for example, we can look at this as rectangles almost. Okay? and we can say that the dots represent their length. The number of dots is the size of their length or width. Okay, so here we have 1 times 2. We can calculate the rows and columns, okay, just like how we calculate the length and the width of a rectangle. Here we have 2 times 4. Okay. Here we have 3 times 6. Okay. And here we have, of course, 4 times 8. Okay. So we can write it down here. T1 is 1 times 2. T2 is 2 times 4. T3 is 3 times 6. T4 is 4 times 8. Okay. Now, this one's a little trickier than our previous sequence. What is the pattern here? Okay. You can pause the video and think it through yourself. Okay. Now, look at the factors here. We notice that with each subsequent term in the sequence, one of the factors increases by 1, another one increases by 2. Okay? So because it's a constant increase, the factor is acting like a arithmetic sequence. But we can't really say this is an arithmetic sequence because it's not increasing by a constant value. Okay? But we can rewrite this as Tn, if it's the product of two factors. Okay? Our first term, we have 1, so we can represent that as n. And our second one is 2. And for T2 it's 4, for T3 it's 6, for T4 it's 8, etc. So we can represent that as 2n. Okay? Now, let's verify our answer to see if our general formula works for the sequence. Okay? Now, for T1 we have 1 times 2 times 1. Okay? And that'll just be 1 times 2, and that gives us 2. Let's try T3. Okay? For T3 we have 3 times 2 times 3, okay, which is the same thing as 3 times 6, which is 18. Okay? Let's try it one more time. We'll use T4. Okay? T4 would be 4 times 2 times 4, and that gives us 4 times 8. And 4 times 8, of course, is 32. So you can look back at the diagram. We know that T1 is equal to 2, T3 is equal to 18, and T4 is equal to 32. So we know that through verification, we know that the general formula for the sequence is Tn equals n times 2n. Okay? Now we can also find the value of other terms. Okay? So, as practice, okay, you can find T12, okay, and find a term where we can say Tn, find what the value of n is equal to 200. Okay, so you can pause the video and try doing this practice questions. Okay, to summarize, geometric sequences are usually written in the form of a plus b to the power of n minus 1. We can use any letters here, but I'm using a and b just because I find it easier. A is the first term, and b is the factor by which it is multiplied. Now remember, why do we have n minus 1? Because when we have our first term, it is not being multiplied by anything yet. So, sorry, this should be written as times Okay? For our first term, it's not multiplied by anything, so when our n equals 1 in our first term, and 1 minus 1 is 0, any number to the power of 0 is equal to 1. Okay? That's why we have a times b to the power of n minus 1. Okay, when finding the general term from a diagram, find a pattern, okay? Check and see if it's arithmetic or geometric or something else, okay? And then construct, and the constant. Okay, in other words, the first term, okay? It always helps to verify your answer if possible. Okay. All right, so that is it for today's lesson. Thank you.